Okay. So last week we studied how to evaluate the temperature distribution within a fin and the rate of heat transfer to a fin. So there are 4 different cases, and depending on these assumptions, and these are temperature distributions and fin heat transfer rate. So today we are going to study how to, evaluate the performance of this fin. So there are 2 properties, 2 parameters that we can use to evaluate the performance of a fin. One is a fin effectiveness, and the other one is fin efficiency. So we are going to study, the fin effectiveness and fin efficiency. The easiest way to understand the difference between fin efficiency and fin effectiveness is when you design a fin like this, and let's say the base is going to be at high temperature, 100 degrees Celsius, and the surrounding fluid is at low temperature, 20 degrees Celsius. Then we install this fin trying to increase the surface area where heat transfer takes place. So ideally, we want to have a heat transfer from the fin to the surrounding fluid in this way. So every surface of the fin is going to be at 100 degrees Celsius. So that we can have a heat transfer from the fin to the surroundings, Q by this equation, HA times 100 degrees Celsius minus 20 degrees Celsius. This is the ideal case. But in reality, because of the heat transfer from the base in the direction of the fin, there is a temperature decay. Am I recording this? Okay. There's a temperature decay. So from here, this is 90 degrees Celsius, 80, 70, 60, 50, 40, etc. So there is a temperature decay. So the actual heat transfer from the fin to the surrounding is going to be less than the ideal case. In this ideal case, we have a uniform heat transfer because of the temperature of the surface of the fin is going to be uniform. But in this case, the heat transfer by convection from the surface of the fin to the surrounding air is going to decrease in the direction of the fin because the temperature of the fin is going to decrease. So this is what happens. So this is the actual fin. This is the ideal fin. Then what is the worst case in terms of heat transfer when we don't have a fin? Then the surface is going to be 100 degrees Celsius, and there's a heat transfer to the surrounding fluid in this way. The ideal case, the actual fin, and this is the worst case in terms of heat transfer because we don't have a fin. So if you want to compare whether a fin is useful or not, you can compare this one and this one. So this is fin effectiveness. Then you can also, determine how good this fin is in comparison with the ideal fin. That comparison is going to be fin efficiency. So this is fin efficiency. And this is effectiveness. Then how can you compare? You can compare when there's a fin, so fin heat transfer rate Q by F, and the fin without the heat transfer without a fin. Let's say this one is Q without fin. So if you calculate the rate of heat transfer with a fin divided by the rate of heat transfer without fin, this is fin effectiveness. Then what about here? The efficiency can be determined by the rate of heat transfer from a fin, this one, compared to the maximum possible heat transfer when the surface of this fin is at a uniform temperature at 100 degrees Celsius. Then that's when we have the maximum rate of heat transfer, which is Q by max. So that's how we can determine fin efficiency and fin effectiveness. Then, how can we determine this Q by F? So these two can be found from a table. What table? This table, table 3.4. Then what about this Q by max? This Q by max can be determined by the Newton's law of cooling, which is H, the convection heat transfer coefficient, times the area of the fin. So the entire area of the fin times temperature difference. Temperature of the surface which is the same as the temperature of the base. So this 100 degrees Celsius is going to be temperature of the base. So this is temperature of the base. 100 degrees Celsius is the temperature of the base, and 20 degrees Celsius is the temperature of the surrounding fluid, T infinite. So Tb minus T infinite. Now that's how we can determine the maximum rate of heat transfer from the fin to the surroundings. What about this Q without a fin? Can be determined by H, the same convection heat transfer coefficient, times the area, since there's no fin, area of the base, which is the base surface area, times Tb minus T infinite. So that's how we evaluate the performance of a fin. So by determining the fin effectiveness, we can see whether it is the worth to install a fin or not. And by the calculating the fin efficiency, you can say whether the fin is well designed or not. Okay. So that's how we can evaluate the performance of a fin. So let's talk about this fin efficiency, fin effectiveness. So when we determine whether it is worth to, add a fin, we need to, evaluate the fin effectiveness, and this fin effectiveness should be at least 2 or above to be useful. And, of course, the fin effectiveness should be as large as possible. Okay. Then what about then how to, have an effective fin? The thermal conductivity of the fin should be as high as possible so that we can increase the rate of heat transfer by conduction. If you increase the rate of heat transfer by conduction, the temperature decay in the fin is going to be less. So instead of, the 100, 90, 80, 60, 40, if you use a highly conductive material to build this fin, the temperature decay is going to be maybe 100, 95, 90, 85, 80, etc. So you can minimize the temperature decay that will make the fin to be, the close to this ideal case. So one way to, to make an efficient, the fin is going to be, we should, use a highly conductive material. And the cross-sectional area per parameter should be as low as possible. It means that trying to make this fin as thick as possible so that, you have a large cross-sectional area for the, the conduction heat transfer. And it's going to be more effective when H is smaller. So all three, the conditions are, the trying to, the maximize the conduction heat transfer so that, that you can, the minimize the temperature decay. In this way, trying to be as consistent as possible. In that way, you can, have an efficient fin. Okay. So that's how we evaluate the performance of a single fin. In reality, in many engineering applications, we use a number of fins. Then how can we analyze fins? Gonna be, the pretty simple. So if you have a base surface, and let's say that you are going to install, the several fins on this surface. Let's say 1, 2, and 3. Then how can we determine the rate of heat transfer, Q? This rate of heat transfer by Q should be determined by Q by the fin plus Q without a fin, which means we are going to calculate Q by F from each fin, Q by F. And between fins, we have a surface, base surface is open to the atmosphere. So this is going to be Q without fin. So the total heat transfer Q should be the sum of fin heat transfer rate and the rate of heat transfer from the base surface, which is not covered by fins. Okay. Then how can we calculate this one? This one is from table 3.4, which is this table. And this Q without a fin can be determined by convection heat transfer coefficient H times area, the base surface area, minus the area which is not covered, which is covered by the fin, times temperature difference, times temperature of the base minus temperature of the surrounding fluid. So that's how we can determine the rate of heat transfer without a fin, and we can calculate this fin heat transfer rate directly from a table. You can also use the fin efficiency to determine this. If you use that, it's going to be this one. The total heat transfer rate is going to be the number of fin N times the fin efficiency times convection heat transfer coefficient times the fin area times theta B, which is the temperature difference, TB minus T infinite, plus H times the base surface area times theta B, which is again TB minus T infinite. And this equation is exactly the same as the sum of these two. So either way is fine. If you want to use fin efficiency, you can use this equation, or you can calculate fin heat transfer rate directly from a table and calculate the heat transfer rate between fins by using this equation. Either way, fine. Okay. So that's how we can analyze the rate of heat transfer from a finned surface. We have one problem we can study together. We have a turbine blades. We have turbine blades mounted on a rotating disc in a gas turbine engine. So what is it? So when we have a turbine, there's an inlet. There's an exit. And there's a shaft that will produce power, W dot out. And there are turbine blades installed like that. So what's going to happen is that high pressure, high temperature, high temperature steam enters this turbine through the inlet. Since it is under high pressure, under high temperature, what is going to happen? It's going to expand. So while it is expanding, it's going to push each turbine blades. So that's how we can produce this shaft power. And the steam is passing this way and then goes out. So while doing so, it's going to rotate this shaft. And each turbine blade is this one. Okay? So we can use a fin analysis to determine the rate of heat transfer from this each single blade. That's what we are going to do. Okay. So whatever the gas should be at extremely high pressure and temperature. And what is the temperature of the gas? 1200 degrees Celsius. So we have this turbine blade, which is going to be a fin, which is going to look like a fin. And the surrounding fluid is going to be at 1200 degrees Celsius. And the convection heat transfer coefficient H is going to be 250 watt per meter square. Kelvin. Just to give you an idea about this H value, the H value of this air in this classroom is going to be approximately, the 5 or less than 10. That is the convection heat transfer from the air in the classroom to you, or from you to the air in the classroom. So 250 is going to be whether you have a gas and with extremely, the high velocity, or a liquid which has almost no velocity, then H value is going to be close to 250. Just to give you an idea about, what this H value means in reality. And the thermal conductivity of this fin is going to be 20 watt per meter Kelvin. So the thermal conductivity K of this one is going to be 20 watt per meter Kelvin. Stainless steel has a thermal conductivity value of 19 watt per meter Kelvin approximately. So this material is going to be, a metal alloy, made of, the stainless steel. Just for your information, the thermal conductivity of copper is going to be approximately 400 watt per meter Kelvin. So you can get the idea about, what is 20 watt per meter Kelvin. Usually the insulation or plastic, they have a thermal conductivity value close to 0.1 watt per meter Kelvin. So 20 watt per meter Kelvin is quite high, okay? Not extremely high, but relatively high. Have a length of 50 millimeters. So this length is going to be 50 millimeters, but do not use millimeters. You convert to whatever the unit you are familiar with. So I'm going to use meter. So 0.05 meter. The cross-sectional area in this one, A of C is going to be 6 times 10 to minus 4 square meter. And the parameter is going to be 110 millimeters. So P is going to be 0.11 meter. And the temperature of the shaft. So this is going to be the shaft. This is going to be the turbine blade. The shaft temperature, which is the temperature at the base. So the base temperature, this one, T of B is 300 degrees Celsius. If the maximum allowable blade temperature is 1050 degrees Celsius, what does it mean? Above 1050 degrees Celsius, this material cannot withstand above this temperature, so this turbine blade is going to fail. What is the maximum allowable temperature of stainless steel? just for your information. Around 650 degrees Celsius. Above this temperature, the stainless steel is going to be okay for, the several uses. But, for a long time, it's going to be, the fail. That is called fatigue. Heard about it, right? The blade tip may be assumed to be adiabatic. So there is information. There is information about, what kind of case we are going to use in a table. So this is the clue for, the table. You remember in a table, there are 4 different cases. Case A, B, C, and D. So to select, which case we are going to use for our heat transfer problem, we need to make an assumption for the tip condition, and that is given here, adiabatic. We are going to use it later. The maximum possible blade temperature is going to be 1050. That means, please assume that the maximum temperature of the fin is going to be 1050. And which location in the fin should be the maximum temperature? Near the base? What is the heat transfer, the phenomenon here? The surrounding is 1200 and the base is 300. So what is the heat transfer direction? From the gas to the shaft, right? So the heat transfer direction is going to be from the gas to the shaft. So there's a heat transfer by convection to the surface of the fin, and within the fin, there is a heat transfer in this direction by conduction. So which location has the highest temperature in the fin? According to the second law of thermodynamics, heat transfers from a higher temperature point to a lower temperature point. So the maximum temperature should be at the tip. So our assumption is that the temperature at the tip is going to be 1050 degrees Celsius. So let's solve this problem. So this is the condition. Then what we want to check is the temperature at the tip. So we can use this table, and what was the case? We assume that the tip is going to be adiabatic. So our case is going to be case B. We can use either this equation for temperature, this equation for heat transfer rate. So what is our interest? Do we want to determine the heat transfer rate or temperature? We want to know whether the temperature at the tip is greater than this one or less than this one. So we want to know the temperature distribution in the fin. So this is our equation. So let me write this equation here. Then what is the temperature distribution? Theta over theta B. Theta over theta B is going to be hyperbolic cosine, the cosine H, m times L minus X. Divided by cosine H, m times L. If you look at this equation, the first thing you may want to ask is, what is theta? What is m? I know what is L. It's going to be the length of the length of the fin X is going to be the location in the fin. But what is M? What is theta? If you want to know, you go back to the table and look at the bottom of the table. Theta is T minus T infinite. So this theta is going to be T minus T infinite divided by what is theta B? Theta B is TB minus T infinite. TB minus T infinite is going to be cosine H, and we have a M. What is M? M square is HP over KA. M is going to be HP over KA of C times L minus X divided by cosine H. This time we have M HP over KA of C. Oh, by the way, we have a square root. Square root. Square root. Times L. So this is the equation. Then let's solve this equation. What is the T infinite? 1200. So this one is 1200. This one is 1200. What is the base temperature? 300. Then, what is the temperature, that we want to determine? The temperature at the tip. So what is X? X starts from the base. This is X. So when X is the length of the fin, then it's going to be at the tip. So X is going to be L. X is going to be L. L minus L is going to be 0. What is cosine 0? 1. But by the way, this is not cosine. It's a hyperbolic cosine. Cosine H. You may want to, read your manual of your calculator and make sure you know how to determine this cosine H. What about here? L is going to be 0.05 meter. H is 250. Parameter is 0.11. Thermal conductivity is 20. Cross-sectional area is 6 times 10 to minus 4. So we have everything. Can we determine the temperature? Yes, we can. If you do the calculation, the temperature is going to be 1037 degrees Celsius. Now, this temperature is less than 1050. So this cooling application is okay because the temperature at the tip is less than the maximum possible temperature of the the fin. So this is okay. Then what is the second question? Then what is the rate at which heat is transferred from each blade to the coolant? That means, what is the fin heat transfer rate? And how can we determine fin heat transfer rate? This is the fin heat transfer rate. So Q by a fin can be determined by capital M, hyperbolic tangent, tangent H, M times L. Then I don't know what is this capital M. Then you can go to the the bottom of the table, and there is capital M, square root of HPK of C times theta B. So this one is going to be square root of HPK A of C times theta B. Then what is theta B? TB minus T infinite. What about this M? Square root of HP K A of C. Then let's solve this problem. What is H? 250. What is the parameter? 0.11. What is K? 20. What is A of C? 6 times 10 to minus 4. The base temperature, 300. The surrounding fluid, 1200. Again, H, 250. Parameter, 0.11. Thermal conductivity, 20. Cross-sectional area, 6 times 10 to minus 4. The length of the fin is 0.05. So we have everything. Can you determine the fin heat transfer rate? Yes, we can. It's going to be minus 508 watt. Why there is a negative sign? This is the heat rate of heat transfer from the fin to the surrounding, but the heat transfer direction is from the surrounding gas to the fin. That's why there is a negative sign. Okay? Any question? You mean the cross-sectional area? Doesn't matter. As long as you know the cross-sectional area and parameter. Because what matters is on the surface, we assume that there is a convection heat transfer. The rate of heat transfer by convection from a square shape or the circular shape, they are about the same, as long as you have the same surface area. Any question? Yes. Part A and part B? Oh, you mean, the case A, B, C, D? Yeah. Because according to the problem statement, the first one is we need to determine the temperature. The second one is we need to determine the heat transfer rate. So whenever there's a heat transfer problem, what you want to determine is going to be either heat transfer rate or temperature. So only these two. So if you look at the table, this one is for temperature. This one is the rate of heat transfer. Any other question? So we studied 3 items in chapter 3. The thermal resistor network and one-dimensional steady-state heat transfer with heat generation. And the last one is going to be this fin. So there are 3 items that you need to, to study to prepare for the second exam. That's everything for chapter 3. We have a new homework assignment, which is going to be due by a week from today. So next Tuesday. And today we are going to study transient conduction. So to study this transient heat conduction, there are a couple of things that we need to know. The first one is the governing equation. What is the governing equation for this conduction? So whenever you see a conduction, the governing equation is called the heat equation. What is the heat equation? Let's talk about the simplest coordinate system, which is a Cartesian coordinate system. Then the governing heat equation is going to be partial over partial x, k partial t over partial x, plus partial over partial y, k partial t over partial y, and partial over partial z, k partial t over partial z, plus heat generation q dot is going to be density times specific heat partial t over partial time. So this is the equation that you are going to use whenever you have a conduction heat transfer. However, solving that equation as is looks very complicated. So what we are going to do? We are going to assume that it is one-dimensional heat transfer, no heat generation, and constant thermal conductivity K. Then let's see what's going to happen. So with these assumptions, we can remove y and z and q dot, and this K comes out. Then you can divide each side by thermal conductivity K. Then, since we know K over density times specific heat is thermal diffusivity alpha, and rho C over K is going to be 1 over alpha, then the governing equation that we are going to solve in this chapter 5 is going to be partial t square over partial x square is going to be 1 over alpha partial temperature over partial time. So that looks much simpler than this general energy balance equation, general heat equation, right? So now the question is, can you solve it? Can I solve it? I don't know. Can you solve it? Maybe you can. But you don't want to solve in its present form. Why is that? We have a second order differential equation in space on the left-hand side, first order differential equation in time on the right-hand side. So this is very complicated. So there is a general solution available, but the general solution is going to be very long. It is longer than the entire building. It is longer than Mount Pleasant. It is longer than the entire Earth because it is infinite. So we don't want to solve that. So there are 2 options. We don't want to solve don't give up. We don't want to solve the exact solution because the exact solution is extremely long. So let me show you the exact solution, just for your information. Oh, there is. No, in front of this. Oh, right here. So the general solution, the exact solution is this one. Looks nice, isn't it? So let me explain what this one is. Theta star means theta is t minus t infinite. Theta star means theta divided by theta I, which is t minus t infinite over ti. What is ti? Texas Instrument? No. Initial temperature. Minus t infinite is going to be what? Sigma, when n is from number 1 to infinite, Cn, by the way, Cn is this one, O sine zeta n divided by 2 zeta n. Oh, this is 1. I'm sorry. Plus sine 2 times zeta 1 times E2 minus zeta 1 square Fourier number. By the way, Fourier number is alpha t over L square and cosine zeta 1 x star. By the way, x star is x over L. So this is number 1. So now let's go to number 2. 4 times sine zeta 2 divided by 2 zeta 2 plus sine 2 times zeta 2 exp minus zeta 2 square Fourier number. By the way, this is the Fourier number. Cosine zeta 2 x star. By the way, x star is x over L plus. Now number 3. 4 times sine zeta 3 and etc. 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 4 times sine zeta 1 million and etc. etc. And now 4 times sine. How? What is the market cap for S&P? $10 trillion. So what I mean is that the exact solution is extremely long. It's unlimited. So do you want to solve it? No. Do I want to solve it? No. So what am I going to do? We are engineers. We want to simplify them, right? So we are going to simplify them. How? Two ways. The first one, I'm going to look at the governing equation. Oh, so it has two components. The second order partial differential equation in space. First order differential equation in time. Which one is more complicated than the other? Left or right? Pick one. Left? Right? Left, probably, because it's a second order. So you can find a way to neglect this one. That is called lumped system. Oh, neglecting this whole left-hand side sounds too extreme. Is it okay in practical application? Yes. In some cases. And in many cases. So that's why we are going to study lumped system analysis, lumped capacitance method, lumped, the method. There are so many names, but whenever you hear lumped, that means we are going to neglect heat transfer in space for transient conduction problem. That's the first thing that we are going to study probably today. And the second one, okay, so that can be an option. When the heat transfer within space is not dominating the entire heat transfer, maybe we can neglect that. Okay, that's fine. But what about the heat transfer within space is significant? Then you cannot neglect that anymore. Then you need to solve this general solution. Then let me give you one, then there are, the couple of ways. There are several ways to simplify that. One is, let's say the exact answer to this sigma star, I'm sorry, not sigma, theta star is 1.9234654325256 etc., etc. Then let me tell you, if the first term represents 1.923, the second term red, so the first term is blue, this one, the second term represents plus 0.00046, and third term represents plus 0.00000, and what is the next one? 54, and the next term represents 0.0000000, and what is the next one? 32. Then, is it really necessary to solve all this, the exact solution? Not really. I will be probably okay, the stop here. The exact solution is 1.92346, etc. I will be okay saying that the solution is going to be just 1.923. Yeah. If you want to buy a car and it says that, it's going to be $50,000 and 23 cents. Are you really, into that 23 cents? No, not really. $50,000, that's important, the numbers, right? So in the same way here, when we talk about transient heat conduction problem, this 1.923, that is, the what matters, not 0.00046. So in this case, we are not going to solve the exact solution. We are going to solve the first term, that is called approximate method. So that's the second part of this transient heat conduction problem. So we are going to solve two of them, lumped method and approximate method. So these are the two items that could be in your second exam, okay? Now you get the idea. Then let's start with the lumped method. And what is the lumped method? We assume that, the time-dependent term dominates the heat transfer, not the heat transfer in space. Okay, I get that, but what is that in reality? So we need to understand, when we can neglect the heat transfer in space. So that means you want to hear an example. Not just an example, it's going to be a good example. So let me give you a good example so that you can understand, the what is lumped method. So basically, we are going to study transient conduction problem. Then what is transient conduction problem? What is the main difference between steady conduction and transient conduction? Steady conduction is like we have a heat transfer from this classroom to the outside. Today, the outside temperature is freezing, 0 degrees Celsius. So the heat transfer is this way, Q. So the indoor is going to be always 20, outdoor is always 0. That is the steady conduction problem. Then what is transient problem? I have a water, the tank that is maintained at 0 degrees Celsius, so it's freezing. And I had a solid whose temperature is 20 It is just dropped into water. So initially 20. After 1 minute, still 20? No. 20 becomes 18, 16, 14, 12, 10, and 8, etc., 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 and 2, etc., and 0, and minus 2. Is that possible? No. The lowest possible temperature is going to be 0, right? So what is the main difference? In transient conduction problem, we have a change in temperature. We have a change in temperature. That's a transient conduction problem. Then let's talk about, this transient conduction problem. The simplest transient conduction problem is going to be, we have this much liquid, this much, the fluid, and there's a solid object. Initially, at 100 degrees Celsius, 100 degrees Celsius, 100 degrees Celsius. Everywhere is 100 degrees Celsius. Surrounding fluid at 20 degrees Celsius. This is a transient problem. Then, what is the heat equation? Partial t square over partial x square is going to be 1 over alpha, partial temperature over partial time. Then, what is the left-hand side? I told you that this one is, the second order differential equation in space. And what is the right-hand side? Is a time-dependent term, right? Then, what it means, space, in this problem. What happens in this problem is going to be, so we have a solid initially at 100 degrees Celsius, and after, let's say, 2 minutes later, and what's going to happen? The solid is at still 100 degrees Celsius, surrounding fluid at 20 degrees Celsius, nothing happens? No, because the solid is at higher temperature than the surrounding, there's a heat transfer from the solid to the surroundings. So there's a Q in any direction, Q, and Q. Then, because of this heat transfer, what do you expect? The temperature of the solid is going to decrease, right? Yeah. Then there are two different cases. One case, the solid is plastic. And the other case, the solid is copper. What is the main difference? Copper has high thermal conductivity. Plastic has low thermal conductivity. So the temperature inside the solid is going to be look like this. Initially, the surrounding area near the surface, the temperature near the surface will drop first. So here is going to be 20, away from the surface still 90, at the center 100, 90 and 20. On the other hand, in this copper block, the thermal conductivity is pretty high, so the heat transfer from the center to the surface is going to be extremely fast. So near the surface, when the heat transfer is really fast, so the center is 90 away from the center 90, 89, 88, etc. Another 2 minutes later, this one is going to be, the center is still at 100 degrees Celsius. Now there's a 80 and 20, 80 and 20. On the other hand, this one, heat transfer inside the solid is very fast. So the center is going to be 80. Away from center, maybe 78. Near the surface, 76. And a while later, now there is a slight change at the center. Now the center is not 100 anymore, maybe 90. Away from the surface, 60. Near the surface, 20, 60, 20. And on the other hand, here, heat transfer in the solid is very fast. So 70, 68, 66. The left-hand side, the temperature gradient from the center of this solid to the surrounding fluid is going to be extreme. So this is the temperature distribution within a system, within the solid. On the other hand, the temperature is almost uniform. So there is a one figure that shows the difference between these two is this one. When a solid exposed to a fluid at extremely low temperature, if the thermal conductivity, the conduction heat transfer within the solid is excellent, then the temperature is going to be almost uniform in the solid. But when the heat transfer by conduction within the solid is not that good, then the center is still hot. Away from the center is going to be pretty low. So there's a significant temperature distribution. Then going back to the governing equation, the left-hand side shows the temperature gradient in the solid. Then, in this case, partial t squared over partial x squared is going to be a significant number. On the other hand, if the temperature is almost uniform, the left-hand side is going to be almost negligible. So, if you have a highly conductive material, then the temperature distribution within that solid is going to be almost uniform. So you don't need to worry about second order differential equation in space. That is called lumped system. If you have a lumped system, you can neglect the left-hand side and you only deal with the right-hand side. That is lumped system. Okay? Then, okay, I get that. When we have almost uniform temperature within a solid, we can assume that that's going to be a lumped system. Then how can we analyze that lumped system? So in reality, transient heat transfer problem, the governing heat equation looks like this. So the temperature T should be in the form of location X and time T. But if you can assume that it's a lumped system, we can neglect spatial effect. So we don't need to worry about this X. The temperature T is going to be just a function of time T. So that is our assumption when we have a lumped system. Then how can we come up with the governing equation? The governing equation is pretty simple. So let's solve this equation. When we have a solid and the surrounding fluid, and we expect that there is a heat transfer, Q. What is this heat transfer? From the solid to the surrounding fluid. Is it conduction, convection, or radiation? It's going to be conduction from a surface to a surrounding fluid. So how can we determine convection heat transfer? H times area times temperature difference. Okay, then can we apply energy balance equation for this heat transfer? Maybe we can. What is the energy balance equation? Energy transfer in minus energy transfer out is going to be the change of energy of a system. Then, what is this Q? In thermodynamics, this Q is Q dot the rate of heat transfer. So let's convert this energy balance equation into the rate of energy balance equation dividing by time T. Then what is the direction of heat transfer? From the solid to the surroundings. So this is Q. So in terms of energy transfer, this Q is going to be what? Energy transfer out, right? So energy transfer in, is there any incoming energy transfer? No, there's only energy transfer out for the amount of H, A, delta T. Then, what about the right-hand side? Do you know how to determine the change of energy of a system? In chapter 3, thermodynamics, for a closed system, we studied it. Unless it's a phase change material, we can use specific heat. Mass times specific heat times temperature difference over delta T. So this one is the change of energy. Then we just need to solve this equation. To solve this equation, let's write this in a differential form. So what is the differential form of this equation? Minus HA, then what is this delta T? The temperature of the solid minus the temperature of the surrounding, T infinite. So this delta T is going to be T minus T infinite. It's going to be mass. Let's use density times volume, which is the same thing. Density times volume times the specific heat. What is delta T over delta T? dt over dt. Then can you integrate this one? Maybe. Let's do that. let's divide each, each side by rho VCP. Rho VCP. Then what do you get? We have dt over d temperature over d time is going to be minus HA over rho VC times T minus T infinite. Can you solve it as is? No, but you can replace this T with theta. So I'm going to say theta is going to be T minus T infinite. Then what is the first derivative of this theta with respect to time? We get d theta is going to be dt minus dt infinite. By the way, t infinite is constant, so this one goes away. So this equation can be rewritten as, what time is it? Oops. d theta over dt is minus HA over rho VC theta. Then multiply each side by dt, and divide by theta. Then what do you get? d theta over theta is going to be minus HA rho VC dt. Then can you solve this equation? Yes, you can integrate that. If you integrate, you get natural log theta is going to be minus HA over rho VC T. Then the solution of this one is going to be theta is E2 minus HA over rho VC T plus some constant. So this is the general solution, and we are going to determine this unknown C this Thursday. So we can use this one equation to determine the change in temperature of a lumped system. V is volume.